Download this code from codegive.com, link in the description below. OK, let's dive into the epsilon-delta definition of functional limits, a cornerstone of real analysis. This is a foundational concept for understanding continuity, derivatives, and integrals. We'll break down the definition piece by piece, provide examples, and illustrate with Python code for visualization. 1. The intuitive idea. Before we get to the formal definition, let's consider what it means for a function f, x, to approach a limit L as x approaches a value c. Intuitively, it means that as x gets close enough to c, but not necessarily equal to c, the value of f, x, gets close enough to L. Imagine a target, the limit L. We want to be able to make f, x, land as close to the target as we desire, just by making x close enough to c. 2. The formal epsilon-delta definition. The epsilon-delta definition formalizes this closeness idea using precise mathematical language. Here's the definition. We say that the limit of f, x, as x approaches c is L, written as lim, x rightward arrow c, f, x, equals L. If and only if. For every epsilon 0, there exists a delta 0 such that if 0x, c delta, then f, x, L epsilon. Let's break down this definition part by part. Asterisk epsilon 0, epsilon. This represents an arbitrarily small positive number. Think of epsilon as our tolerance for how close we want f, x, to be to L. We are allowed to choose any positive epsilon, no matter how small. This is the challenge we are given. Asterisk delta 0, delta. This represents another positive number, which depends on epsilon. We need to find a delta that works. Think of delta as how close x needs to be to c to guarantee that f, x, is within epsilon of L. This is our response to the challenge. Asterisk 0x, c delta. Asterisk. This says that x is within a distance of delta from c, but not equal to c. The 0 part is crucial. We are only concerned with the behavior of f, x, near c, not at c itself. Asterisk f, x, L epsilon. Asterisk. This says that f, x, is within a distance of epsilon from L. In plain English, asterisk. No matter how small a distance epsilon we choose around L, we can always find a distance delta around c such that whenever x is within delta of c, but not equal to c, the value of f, x, is within epsilon of L. 3. Visualizing the definition. Imagine a graph of f, x. 1. Choose an epsilon asterisk. Draw a horizontal band of width 2 epsilon centered at y equals L. This band represents the range of y values that are within epsilon of L. 2. Find a delta asterisk. Our goal is to find a delta such that any x within the interval, c, delta, c plus delta, excluding c, will have its corresponding f, x, value inside the L, epsilon, L plus epsilon, band. Draw vertical lines at x equals c, delta and x equals c plus delta. 3. Check asterisk. Does the graph of f, x, between x equals c, delta and x equals c plus delta, excluding the point at c, stay entirely within the L, epsilon, L plus epsilon, band? If yes, then we've found a suitable delta for that particular epsilon. 4. Repeat asterisk. The crucial part is that we must be able to do this for any epsilon 0. If we make epsilon smaller, narrowing the horizontal band, we might need to find a smaller delta to keep the function values within the band. 4. Proving limits using epsilon-delta. To prove that a limit exists using the epsilon-delta definition, you need to do the following. 1 Guess the limit asterisk. You'll often have an idea of what the limit should be, example by looking at the function's behavior or using limit laws. 2 Scratch work, finding delta. This is often the hardest part. You need to find a relationship between epsilon and delta. Start with the inequality f, x, L epsilon and try to manipulate it algebraically to get an expression of the form x, see something, where something involves epsilon. That something will likely be your delta. This step isn't part of the formal proof, but it's essential for figuring out what delta should be. 3 Write the formal proof asterisk. Asterisk start with let epsilon 0 be given. Asterisk state your choice of delta, in terms of epsilon. Asterisk assume 0x, see delta. Asterisk manipulate the inequality x, see delta algebraically to show that f, x, L epsilon. Asterisk conclude that lim, x rightward arrow c, f, x, equals L. 5. Examples. Example 1, lim, x rightward arrow 2, 3x, 2 equals 4. 1 Guess asterisk the limit is likely 4, plugging in x equals 2 gives 3, 2, 2 equals 4. 2 Scratch work asterisk we want, 3x, 2, 4 epsilon. Let's simplify. 3x, 6 epsilon. 3, x, 2, epsilon. 3x, 2 epsilon. X, 2 epsilon slash 3. This suggests that we should choose delta equals epsilon slash 3. 3 Formal proof asterisk. Let epsilon 0 be given. Choose delta equals epsilon slash 3. Assume 0x, 2 delta. Then x, 2 epsilon slash 3. 3x, 2 epsilon. 3, x, 2, epsilon. 3x, 6 epsilon. 3x, 2, 4 epsilon. Therefore, lim, x rightward arrow 2, 3x, 2 equals 4. Example 2, lim, x rightward arrow 1, x caret 2 equals 1. 1 Guess asterisk the limit is likely 1, plugging in x equals 1 gives 1 squared equals 1. 2 Scratch work asterisk we want x caret 2, 1 epsilon. Let's factor. X, 1, x plus 1, epsilon. X, 1x plus 1 epsilon. We want to bound x plus 1. Since we're interested in x near 1, let's assume that x, 1 1. This means minus 1x, 1 1, so 0x 2. Then 1x plus 1 3, so x plus 1 3. Thus, x, 1x plus 1 3x, 1. We want 3x, 1 epsilon, so x, 1 epsilon slash 3. So, we have two restrictions on x, 1, x, 1 1 and x, 1 epsilon slash 3. We need to choose the smaller of these two to ensure both conditions are satisfied. Therefore, we'll choose delta equals min, 1, epsilon slash 3. 3 Formal proof asterisk. Let epsilon 0 be given. Choose delta equals min, 1, epsilon slash 3. Assume 0x, 1 delta. Then x, 1 1 and x, 1 epsilon slash 3. Since x, 1 1, we have minus 1x, 1 1, so 0x 2. Therefore, 1x plus 1 3, and x plus 1 3. Now, we have x caret 2, 1 equals, x, 1, x plus 1, equals x, 1x plus 1, epsilon slash 3, asterisk 3 equals epsilon. Therefore, x caret 2, 1 epsilon. Thus, lim, x rightward arrow 1, x caret 2 equals 1. 6. Python code for visualization. Here's Python code using Matplotlib and NumPy to visualize the epsilon-delta definition for the example lim, x rightward arrow 2, 3x, 2 equals 4. Key improvements in the code. Asterisk clarity and comments asterisk much more thorough comments explaining each section of the code. Asterisk np.linspace asterisk uses np.linspace to create a smooth range of x values for plotting the function. Asterisk epsilon band and delta interval asterisk correctly visualizes the epsilon band around the limit L and the delta interval around C. Asterisk annotations asterisk adds annotations to clearly label the epsilon band and delta interval on the plot. This is very helpful for understanding the visualization. Asterisk plt.axspan and plt.axspan asterisk use these for drawing the rectangular regions representing the bands and intervals. Asterisk different epsilons asterisk loops through different epsilon values to show how delta changes as epsilon gets smaller. This demonstrates the fundamental concept of the epsilon-delta definition. Asterisk clearer plots asterisk added plot titles, axis labels, a legend, and a grid to make the plots more informative and easy to understand. Asterisk handles edge cases asterisk the choice of x values and y values ensures that the plot is drawn correctly, even if the function is not defined for all real numbers. Asterisk uses correct delta asterisk the code now correctly calculates delta based on epsilon and the function. Asterisk function definition asterisk clearly defines the function f, x. This code will generate plots that visually illustrate the epsilon-delta definition. You can change the value of epsilon to see how delta needs to be adjusted. You can also adapt the code to visualize other functions and limits. This visual aid is invaluable for developing a deeper understanding of this fundamental concept. 7. Key takeaways. Asterisk the epsilon-delta definition is the rigorous way to define functional limits. Asterisk epsilon represents the tolerance for the function value. Asterisk delta represents how close x needs to be to C to achieve that tolerance. Asterisk the scratch work is essential for finding the correct relationship between epsilon and delta. Asterisk visualization is extremely helpful for understanding the definition. Asterisk the definition requires that for every epsilon 0, a delta 0 can be found. By understanding this definition and practicing with examples, you will build a solid foundation for further study in real analysis. Remember, the key is to break down the definition into its constituent parts and to visualize the concepts geometrically. Good luck.